So in this video, we're examining the relationship between linear functions and exponential functions and the differences between those as well. To start off with, what I thought I'd do very quickly is just review graphing exponential functions. We spent a lot of time on this in our functions unit, but it is worth refreshing our memory here since we're going to be doing a lot of the same things towards the end of this video. Notice that this is an exponential function because f of x equals 2 to the x power minus 9. Anytime you have an x in your exponent, you're looking at an exponential function. That is one of our function families that has certain characteristics that we can begin to examine that will allow us to predict what this graph will look like. For example, once I know it's an exponential function, I know it's always going to make the same basic shape. It's going to make a curve like that goes on forever in one direction and in the other direction approaches an asymptote. This asymptote can change locations depending on the specifics of the function, and it could be that our function is flipped upside down or flipped backwards, right and left, but it's always going to make that same basic shape. Once I know my function and I know the basic shape, I ask myself, what is the domain? The domain is what values of x will work in my function. The easiest way to tell that is to see where your graph goes from right to left. Notice it goes to the left forever. It goes to the right forever. Therefore, this function can go anywhere at once along the number line. All x, as long as x is a real number. The range of the function is just a little bit trickier to figure out. In this case, the range tells me where it goes up and down, and this graph is going to go up forever, and it's going to come down to my asymptote, or it's going to start off going down forever and approach my asymptote from the other side. Here again, it could also start up here and come down this way, or start down here and come up this way. Regardless, this asymptote becomes very important. We need to know where that's at. And ours is going to be at -9. This value, when you're in vertex form, always tells you where that asymptote is. So I'm going to draw my asymptote at y equals -9. Remember, asymptotes are important features of the graph, but they are not part of the solution. Therefore, we make them dotted. And there you go. Since I have a positive 2, I know that my graph is going to have something doubled every time. Doubling is getting bigger, so I know that I'm going to start off small, and I'm going to grow faster and faster. Because of that, my range is going to be above this line. All f of x, as long as f of x is greater than that -9. This type of function does not have a vertex, it does not have a line of symmetry, and so that information is complete. The next step I'm going to look at is what values of x to plug in order to get my solution. Since x is by itself as an exponent and there's nothing added onto it or subtracted from it, I always start with 0. 2 to the 0 power would make this a 1. Minus 9 is -8. So 0, -8 is what I'm going to consider to be the starting point for this function. 0, -8. I'm then going to pick points near that. If I put in a 1, 2 to the first is 2, minus 9 is -7. If I put in a 2, 2 to the second is 4, minus 9 is -5. If I put in a 3, 2 to the third is 8, minus 9 is -1. And if I put in a 4, 2 to the fourth is 16, minus 9 is 7. Notice your growth pattern here. You grew by +1 from 0 to 1, +2 from 1 to 2, +4 from 2 to 3, +8 from 3 to 4, and it's safe to assume our next growth will be +16. Using that pattern, I can see that after 0, -8, if I went down to -1, I go down 8, go down 4, go down 2, go down 1. The next in the pattern would be down a half, then down a fourth, down an eighth, and so on. approaching that asymptote forever, but never crossing it. If you're uncertain as to what I just did there with that -1, consider this. 2 to the negative first power says use the reciprocal of 2, which is a half. A half minus 9 would be -8.5. If I use a -2, the reciprocal would be 1/2 squared, which is 1/4 minus 9 would be -8 3/4. You see, exponential functions grow very differently than linear functions do. I have an example of both right here. F of x equals 2x and f of x equals 2 to the x power. And I'm just going to plug in values really quickly to show you the difference. If I put a 0 into 2 times x, I get 0. 2 times 1 would be 2. 2 times 2 would be 4. 2 times 3 would be 6. And 2 times 4 would be 8. Notice that as your x gets bigger by 1, you're increasing by 2 in f of x, or your y, depending if you're using function or equation notation. That's the key characteristic or key trait of a linear function. It always grows at a constant rate of change. And graphically, we would call that a constant slope. But an exponential function doesn't grow like that. 2 to the 0 power is a 1. 2 to the first power is a 2. 2 squared is 4. 2 to the third is 8. And 2 to the 4 is 16. Notice you start off growing by 1, but then you grow by 2, and by 4, and by 8. This is not constant. Can you see a different pattern that might make more sense here? Hopefully, you recognize that what's actually happening is you're multiplying by 2 each time. That's what happens with exponential functions. Every time x gets bigger, you're saying multiply by another 2. That's what's causing this times 2 to happen. Exponential functions have a constant factor. A constant factor by which you multiply. And there again, in this case, that is times 2. Now, in this one, the constant factor is pretty easy to see. If you run into ones that are more complicated, you can always take the new value divided by the previous, and you'll get that constant factor. Check it out. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. There's your constant factor. I'd like you to take just a second and pause the video. I want you to try and find whether these are linear or exponential patterns, and then restart the video and we'll talk about it. I can tell you there's a typo right here that could make a difference as you're beginning to do these. I'm going to keep talking, and I'm going to assume that you've already paused, you've already worked these out, and that you're now ready to hear what the solution is. When I look here, I see a +8 pattern. This is definitely linear and definitely has a slope of 8. But when I look over here, I see +6, +12, +24. Definitely not linear. Instead, what's happening is you've got times 2, times 2, times 2, and times 2. This is an exponential pattern because it grows by a scale factor of 2 each time. Over here, +10, +15, +22.5 certainly doesn't work. But if I take the new divided by the old, I find that each time I'm growing by a factor of 1.5. This is exponential with a factor of 1.5.